Hello and good day to all of you. So we will tackle the problem solving on phase sequences. But before we do that, if you want to have the copy of the problems, you can go to the description tab on this video channel on this video, and then from there you will be transferred to a Word file that compose of the main problems and some practice problems for you to master. Okay, let us read the problem first before we attack the problem. So this is the problem here. You need to find the power factor of the following vectors using a phasor diagram. So these are the following vectors of the voltage and current. V is equal to 50 bar 10, I is equal to 5 bar positive 30 for A, condition A rather, and B, we have voltage is equal to 50 bar 10, and the current is 5 bar negative 20. Okay, let us solve the problem here. So although there are some solutions already here, I will explain it further for you. Okay, first you need to trace down the phasor diagram of these vectors first. But our main goal, or the most important part of a phasor diagram, is just getting the behavior of the angles. And because of that, we can get the angle theta. And please take note, our main goal is the angles, not the magnitude. Simply because the magnitude, if that is 50 million units, so that is already infinite, you cannot draw a very, very, very long line. The main, what matters most is the behavior of the angles. So you have positive 10, so that is in counterclockwise direction. And then positive 30, we have the counterclockwise direction based on the reference. And please take note, in order to understand what I'm talking about here, you need to go back to the basic fundamentals of this topic so that you can have the basic principles and fundamentals before you solve some problems. So here, positive 10, positive 30, so that is the current and the voltage respectively. So get the difference between those angles. So 10 minus 30, you have 20 degree, and our main goal is to get the power factor. So the power factor is cosine of the angle. So that is cosine 20, which is 0.9396. But you do not know, okay, although we have the answer here, we do not know if the angle is lagging or leading. Just go back to the basic principle that we have two important statements there. I lags B for a lagging condition, and I leads V by a certain angle for a leading condition. So we will make use of these statements in order to get the behavior of the angle. And please take note, whatever the reference is always the right of a certain statement. The right of the statement is your reference, while the left of the statement will be your rotating phasor. The rotating phasor will dictate if the angle will lead or lag the reference by a certain theta or angle theta. Okay, let us go here on the angle I and V, and this is the theta here, if you can see on the camera. And I make use of this angle point, which is our reference. And the I will dictate if lagging or leading. Now, since the arrow sign here, okay, I will redraw it. The arrow sign is in this direction. So it means it is a leading condition. So thus, the answer is 0.9396 leading. So please take note of that basic fundamental. Simply because this is 110% sure. Simply because you see the behavior of the angles and how they separate with each other with a certain angle, and then their relationship as well. Okay, let us go to B, 1 point B. The voltage is 50 bar 10, the current is 5 bar negative 20. So the only difference is this current angle negative 20, so it will lag in a clockwise direction. And also, okay, I will redraw this one later. The angle theta is this, okay, up to this, to the current. So getting the numerical value of the power factor, you have theta v minus theta I, 10 minus 20. You can see there on the camera here, and the value here as well. So please take note, this is theta I, by the way, and this is theta v, of course. So the angle is 30 degree. Now you do not know if that is lagging or leading. So go back again to these statements and place the reference. I could say point O, and clear here, okay, that the angle, okay, theta here is simply equal to 30 degree, and it lags the reference by a certain angle theta. So in this case, the answer is simply lagging condition, because the angle theta here with respect to reference B, the I will dictate if that is lag or lead, and it's clear if you turn the angle in a clockwise direction, that is a lagging condition. There is also one thing that you need to know as well. You can get the numerical value here of that angle in a reverse direction. So that is simply 330 degree. Okay, so that is cosine 330. The answer is also 0.866. Okay, we will go forward to the next problem. Okay, let us continue our problem solving on phase sequences. So this is problem number 2. Let us read the problem first. So determine the phase sequence for the set of voltages, which is, I can enumerate it for you. Vn is equal to 200 sine omega t plus 10 degree. Vbn 200 sine omega t minus 230. And Vcn is equal to 200 sine omega t minus 110 degrees. So our main goal here is to solve or to determine what is the sequence of this set of vectors. Okay, let us move forward to the solution. Okay, this solution here, as you can see, we can convert these instantaneous values to its corresponding phasor values or vector values, because we need to determine the angle theta so that we can have the phasor diagram. Please take note, our given here are instantaneous values simply because it is with respect to time. Okay, and then when we convert it to phasor, and we have this formula on a separate lecture, which is from AC circuits, which is the generation of AC voltages. You can check that video there, and you can see the fundamental that we can convert an instantaneous value to phasor value. So it will become like this: 200 bar 10, 200 bar negative 230, and 200 minus 110 degree. And please take note, okay, that we need to divide it by 2. If you can see, you can still recall that the RMS value, whatever the maximum value, divided by square root of 2. And these values here at the left side is your maximum values. So you need to convert it to corresponding RMS. So you need to divide it by square root of 2, definitely. All of these values here. Okay? But, again, take note, when we draw the phasor diagram, the magnitude is not implemented on the, or it's not prioritized on a phasor diagram, because in a phasor diagram, we usually determining or seeing the behavior of the angle. So, therefore, you need to divide it by square root of 2 to get the RMS value of AN, BN, and CN respectively. Okay, but anyway, our main goal is these angles here. Okay, so let us go to the phasor diagram, and I already draw the phasor diagram here. So you need to get VBN first. That is VAN rather. Positive 10. Yes, this is the positive 10. You have VAN. Next, negative 230. So from the reference here, okay, I will redraw it again. Okay, that is negative 230 degree. Okay, because this is 180, half of the revolution, 270. Okay, and then you have negative 230 there. And next is negative 110. So you have your 90 here, okay, 90 degree. And then this is actually 20 degree. Okay, so from here up to here, you have negative 110 degree. So you can check it out if the angles between the voltages VCN, VAN, and VBN are 120 degrees with respect to each other. So here, we already checked from VAN, this is 80 degree, and this is 40 degree. So thus, this is a 120 degree. Okay. And then, now, from VAN to VCN, that is VAN to VBN, rather. So from VAN to VCN, you have 10, you have 90, you have 20. So if you add it up, yes, this is 120 degree. Okay. And last but not the least, if you want to know the angle between VCN and VBN, it's clear. So you have here 70 degree, because 20 plus 70 is 90, 70. And then you have 50 here. Okay, 50 plus 40 is 90. So from here to here is 120 degree. So this is okay. So thus they are 120 degrees. So see the sequence A, C, B sequence. So the answer is an ACB sequence. So hopefully you understand how to draw the phasor diagram here, and we will make use of that on the next few problems. Okay, hello once again. So let us continue our discussion on phase sequences, and we are in problem number 3. Okay, this is the problem. Given a vector of VBN is equal to 110 bar 30, positive 30, we need to find the other vectors VAN and VCN, assuming a positive or ABC sequence. So to understand this one, so let us have the reference vector. There must be always a reference vector so that you can get the other vectors. So from there, you can use a phasor diagram to locate those angles or those vectors A and Cn. So positive sequence. So recall, if you have a positive sequence, you have an ABC clockwise system. So required is what is VAN and VCN respectively. So what I will do here is I need to have the VBN first located. So you have the reference vector. We will start at the first quadrant here and then rotate the 30 degree positive in a counterclockwise direction. So you have VBN. Please take note, we will prioritize angles instead of magnitudes. So we have the VBN vector there. Okay, next. So to locate the other vectors, we must have the ABC sequence. So please take note, it's like in the alphabet, it must be in a sequence. So you have A, the next letter is B, the next letter is C. So it will begin again at A here. So you have A, B, C, and then A. So since you have only 3 vectors. So the next letter for B in a clockwise direction is C. And please take note, this is a balance system. So they must be 120 degrees apart. So if this is 30, okay, you add 90 degree, this right angle here, and then 90 plus 30 is 120. So you expect the VCN vector here. Okay, so I will have this in a blue marker so that you can see that this is a different vector. Okay, and then the next letter is A. So it must be 120 degree from C and B. So you can locate the vector A at this quadrant here. Okay, so let us have this at the second quadrant. So you have here, it's definitely, you have 60. So another 60 here will give you AN. So okay, we'll have the vector here. Okay, like this. Okay, so this one is VAN. So if this is 60 as well, you have 120. We can check it out. This is 90 and 30. And then this one is 120, as you can see here. Okay. Thus, we have all of the vectors. Therefore, we can now get VAN here. Same magnitude, 110. And then, you have here 30 degree. Okay. Plus 120. So, from here, this is positive 150. So, the answer here is positive 150. And then, for VCN, it's also clear that this is negative 90 from the respective reference. So, you have the same magnitude and then negative 90. So you can observe those angles, if that is leading or lagging, depends on the reference. Please take note, you must have a reference. And then from there, you have in a clockwise or counterclockwise direction. So counterclockwise means positive and clockwise means negative value. So thus, this is the answer for number 3. VAN is 110 bar 150 and VCN 110 bar negative 19. Please take note, balanced polyphase, they have the same magnitude. Okay, let us go forward to problem number 4. Okay, let us conclude our last number for phase sequences. So this is the last number. So given the voltage VCB, which is 120 bar 45, we need to find the value of the phase voltage at phase A if the sequence given is a negative sequence. So here's the solution for problem number 4. We can present two solutions here. You can use the phasor diagrams that we use on problems 1, 2, and 3, or the vector diagrams, or you can use a mathematical equation instead. So it means based on the fundamentals that we have discussed on the last slide or on the last lesson. Okay, so for this, we need to have the given first. So VCB 120 bar 45, and it is the sequence is negative sequence, so that is an ACB, clockwise direction sequence, and then required what is VAN, or the phase voltage at phase A. Okay, now let us recall some equations here. First, this equation. We need to make use of that simply because that is the relationship of the line voltage and the phase voltage. And as we have mentioned, it is lagging by a certain angle, which is 30 degree, and an ACB sequence. Also, in order to have this formula, it must have the same phase. For example, our main goal here is line voltage, and please take note what we have discussed so far, that we need to have the same polarity marks. Otherwise, if that is not the same letter sequence, you need to anti-phase it, which is again based from the basic fundamentals that we have learned on AC circuits. So if this is VBC, which is a line voltage at phase B, it must be the same at the phase voltage at phase B. And then from there, if we get ready computed for BBN, we can now locate VAN with ease using a phasor diagram or a statement diagram. So in that case, you have line voltage at B and phase voltage at B. Our main goal or the plan of attack is get VBN first. Okay, before we do that, as you can see here, it's very obvious that we need to anti-phase vector VCB. So to anti-phase that, you need to recall our basic fundamental that we can have the anti-phase in the magnitude part or at the angle part, having plus or minus 180 degree. So what I will do is, I already have VBC here, but I need to select if plus or minus 180. Okay, now it's my choice. You can do the positive if you want. I choose here negative 180. So negative 180 plus 45 is, the vector VBC is 120 bar negative 135. Okay, let us move forward. So using this formula here, okay, that we already have vector VBC and we need to get VBN. So it must be lagging by 30 because an ACB sequence. So thus, manipulating this equation here and getting the answer in tertiary calculator, the answer is 69.28 minus 105 degree. Okay, however, this is from the basic fundamental or principle. You need to revisit that in a negative sequence, because they recall VAN will leads VCN will leads VBN by 120 degree, if you can still recall. Very obvious, if that is ACB, the next letter again is A. So, the transition from B to A. So, thus, B will leads VAN again by 120 degree. Okay? However, we can change, or this is the same with this statement, that VAN lags VBN by 120. We just change the reference. Because here, VBN with respect to VAN, since we are given with BBN, thus we need to have the reference VBN instead of VAN. So instead of leading, it will become lags. So when you say lags, again, plus is lead, while minus is lags. So thus, you need to get VAN given BBN, you need to have a lagging condition of 120. And using that statement, we can now proceed to the answer here that VAN is simply equal to 69.28 degree, negative 225, or if you add 360 here, this is the same answer as positive 135 on the angle displacement. So, it's your choice. You can use the vector diagram, or you can use these mathematical equations, or the equations or fundamentals that we have discussed on the less fundamental lesson. So again, the next topic will be balanced polyphase systems and the corresponding problems and principles. So, see you there. Ciao at maraming pong salamat.